absent in the other room. Okay, so how would I take out one of those parts of my expression and replace it with a variable? What would it look like? Think back up to this example. Just choose one spot and take that number out. 4?
6.1 minus x equals 1.1.
Perfect. 6.1 minus x equals 1.1. So that's the same as just having a blank, like you've done since first grade. But instead of a blank, you put a variable there. So I'm going to try the second one. 8.
2.4 equals x.
That works. 3.7 plus 2.4 equals x. You could replace any of those with the x. So you could have done x plus 2.4 equals 6.1. Could replace any of those to make your open sentence. It says, are your numerical equations true? Do we have true problems here? 12? Yes. How do we know? How do we know for sure that that's true? I'm gonna actually, let's erase the second one. I want to give a different example than that one. I'm going to do one more similar to the one that we did up on the top part. So this one is 35 times 2 equals 7 times 10. Now somebody show me how to replace one of those numbers with a variable on the other side for the open sentence. 13?
x2 plus 7 equals 7 times 10.
Good, so you're replacing the 35 with the x. So we would, usually when we write a variable with a number being multiplied, we usually put the number first. So instead of saying x2, we would say 2x equals 7 times 10. Good. So how do we know that our numerical equations are true? What would have to be, we have that equal sign in the middle, right? So what do we have to have on both sides of our equal sign? 14?
They both have to be equal on sides. You have to have numbers equal the same number.
Right. If we worked this out, it would be 1.1. So this is 1.1 and this is 1.1. So they're equal. If we work this out, we get 70. If we work this out, we get 70. So we have the same number on both sides of our equal sign. So we know they're true. Both sides of the equals symbol have the same value. Now looking at our open sentences, are those still true? Are they true or are they not true, or can we not even tell? 4?
They are true.
And how do you know for sure that they're true? do we know what x is?
No.
So do we know if they're true?
No.
Can we tell for sure if the open sentences are true right now?
No.
No, we can't. Because what if I put a 10 here? Would it still be true? If I said x equals 10 in both of these situations, would either of those be true then? No. So when it's a variable, we can't tell. We don't know. So we could say we can't tell because the variable can be any number. So until we figure out what that number needs to be, we don't know.
Is that all of this list?
Next page. We have a next page still. So let's turn the page 180. So on this page, we are going to be doing using some patterns in algebraic expressions or equations. So if we look here, it says number 1, for parts A through C, do the following. Look for a pattern in each set of numerical equations. So we have 3 problems that actually have, there's no variable, we know the answers, we know all the numbers. We're describing the pattern in words, and then we're using a variable and to write an equation that represents the pattern. So if we look at our example here, we have 4 plus 0 equals 4, 17 plus 0 equals 17, 243 plus 0 equals 243. And the description says that the sum of any number and 0 is that number. So if we add any number in the whole world plus 0, you're going to still have the same number, right? So that's the pattern. So then they put in the variable of p to stand for that any number. When you see any number, that means variable. So any number and 0, you're going to end up with that same number. That's why there are 2 variables in this problem. Because whatever p is here, it's going to stay the same here. Could be 152, could be 1,000,005, could be whatever number it needs to be. If you add 0 to it, you're still going to keep that same number as your answer. So p plus 0 equals p. That's your pattern. So whatever you plug in there is going to follow the same pattern. That's what that generalizes mean. Generalizing means that you're using it in more than one situation. So when we talk about generalizing behaviors, like you know that you're in every setting, you're not supposed to do certain things. Or at home you may be able to chew gum, but at school you're not supposed to chew gum. So that's generalizing, knowing the different situations in the different settings. So this one, generalizing the pattern, we're saying that every time you do this, it's going to be the same pattern for the problem. So letter A, 18 times 1 equals 18, 2.75 times 1 equals 2.75, 6/10 times 1 equals 6/10. So what's happening in each of those equations? What's the pattern that we're seeing in those equations? Seven.
Anything times 1 equals itself.
Anything multiplied times 1 is going to be itself. Good. So we're going to use these mathematical words. So if we're multiplying, what's my answer called? Like up here we said sum because it was an addition problem. What's the answer to a multiplication problem called? Everyone?
Product.
Product. Good. So the product of what? How am I going to finish that description? The product of 8. Good. The product of any number. So if you see any number, what's that telling you that is? A little more specifically. 13? The variable. So that's going to be our variable. 15, I need you to focus, please. The product of any number and 1 is that, and I'm running out of room, so I'm going to use the number sign, is that number. So any number times 1, you will keep that same number. So now, using a variable, how am I going to generalize that pattern? Let's say x is our variable. So the product of any number and 1 is that same number. So what's that pattern equation going to look like? 12? X times 1. And I'm going to use the dot for the time since we're using x. Times 1 equals x. Remember that from that one Canvas assignment, that if you see that dot up in the air in between there, that means multiplication. So the product of any number and 1 is that number, and our variable equation is x times 1 equals x. 15. You take your head down. You need to be following along with us. Letter B. We have 6 times 0 equals 0. 1/2 times 0 equals 0. 78.7 times 0 equals 0. What's my pattern happening every time? Nine? Uh-huh. Okay, so use it in this kind of format of that sentence. So we are multiplying, so we're going to talk about the what? The product. So the product of and is it just a specific number? What is it then? Well, what's 0 being multiplied by? 7? Any number. So we're multiplying 0 times anything, and we're always ending up with 0. So we would say the product of any number and 0 is 0. So no matter what number we multiply times 0, we always end up with 0. So now how are we going to generalize the pattern? Put your variable in place of that any number. What's it going to look like? 2?
Could you say like x times 0 equals 0?
Perfect. X times 0 equals 0. So whatever number you put in place for x, it's going to follow that pattern. Doesn't matter what that number is. Good job. Letter C. We have 5 times 1/5 equals 1. 100 times 1/100th equals 1. 1,205 times 1 over 1,205 equals 1. And it says the variable in this pattern cannot equal 0 because division by 0 is not defined. So that's something you can't do. You can't divide by 0. That doesn't make any sense, right? You can't divide by nothing. So that means that you can't, so the variable cannot equal 0 is the only difference in this pattern. So what's happening in these equations? What do you see happening? 8? It is. So a 5, if I turn that into a fraction, what's it look like? What do I need to do to it? 12? Put it over 1. So I would have 5 over 1 times 1 over 5. What's that called? Does anybody remember that when you flip it? What's the mathematical term for when you flip the number? Talked about this when we did keep, change, flip. Starts with an R. An R-E. Say 11?
Is it reciprocal?
It is. It is reciprocal. Yes. Good job. Reciprocal. That means where you flip your numbers on the fraction. So we have 5 over 1 times 1 over 5. We have, if we put that as a fraction, we would have 100 over 1 times 1 over 100. So what is happening here? Yes, 12.
You see the product of any number and its reciprocal is 1.
Perfect. Good job. The product of any, I'm going to use a number sign to save space, any number and its reciprocal is 1. So any number that you could use, if you did 72, you could say 72 over 1 times 1 over 72 would give you 1, because you're going to end up with the same number in your numerator and in your denominator, which always gives you 1 whole, right? If we multiplied this across, we would end up with 1,205 over 1,205, which is the same thing as 1. So any number times its reciprocal is 1. So now, how can I generalize that with my variable? Where would my variable fit into the pattern? Think about which, if we look at this first problem, what part of this problem could be anything? Can I change around the 1s, or should I change around the 5s? 14? The 5s, right. That's the part that's changing each time, right? The 5 and 5 here turns into 100, and 100 here turns into 1,205 in both of those places. So that's where my variable is going to plug in, right? Because that can change. So I'm going to say, what's my sentence going to look like then? 13? X times 1 over x equals 1. And then, since it says that the variable cannot equal 0, I'm going to add in x cannot equal 0. So that means that any other number that you could use would work, but we cannot use 0. Does everybody know what that symbol means? Everybody know? It means either cannot equal or does not equal to the other side. So when we use it in this situation, we're saying that x does not ever be a 0. Okay? All right. Let's see if we can. Let's see. List 3 numbers that would make this equation true. A minus A equals 0. So what could I plug in for A to make that sentence true? 8? 3, yeah. What else? 17? 1. Does it have to be any specific number?
No.
Could be any number, right? Pretty much any, as long as it's a positive number, right? We don't know how to do like -3 minus -3. But we don't know how to do that yet, so we don't know if that would equal 0. So I'm just going to put any positive number. Could be 1/2 minus 1/2 would give you 0. It could be 151 minus 151 gives you 0. So any positive number that you can plug in there is going to give you 0. Because you have 2 A's, so you know that they both have to be the same number. Yes, 16.
My dad told me once that a negative minus a number equals positive.
Don't worry about that for now. We'll get there. We'll get to that. Yes, negative numbers, when you're adding and subtracting with negative numbers, there's a whole new set of rules to follow. So we'll figure that out when we get there.
Will we learn that? Like next.
I think we touch on it, but I don't know how deep into it we go. Since I haven't gone past this unit because last year we left school and then we didn't learn anything new. So I didn't do the next units after that. So, and since this is my only my second year in here, I haven't done the other units yet. But anyway, let's see. Let's go to number 3 real quick here. For each equation below, decide how many numbers will make the equation true. So is there only a specific number? Are there tons of numbers that we can use, or will nothing make it true? So letter A, 2 plus B equals B plus 2. So if we plug in numbers for B, we have 2 B's, so both of those have to be the same number. Is there a lot of numbers that can make that true? No numbers that can make that true, or only one specific answer? 12? Many. If I put 0 for B, 2 plus 0 equals 0 plus 2, that works. If I put 11 for B, 2 plus 11 equals 11 plus 2, that works. So yes, there are many, pretty much any number you put in there, again besides negatives, would get you the same thing. Letter B, D times 5 equals 5 times D. Is there only one specific number that could fit in there? Lots of different ones, or will nothing make that true? 4? Many. Again, what's that called where we can flip things and it's going to give us the same answer? What property is that?
Why do you keep on doing this?
Because you're supposed to remember it. Starts with a C. 8.
Commutative property?
Commutative property is that flip-flop for addition and multiplication. Doesn't matter what order you do it in, you're going to get the same answer. So if we have the same numbers on both sides of our addition and multiplication problem, it's going to be equal. So we could use any number to go in there. Letter C, F minus 4 equals F minus 3. Is that going to be lots of different answers, no answers at all, or just one specific number that would fit in there? $12? None. Is there any number that I could put in both of these places that I could minus 4 and minus 3 and still get the same answer?
No.
No, that doesn't make any sense, right? So no number would fit in there because they would have to be the same. If it was an F and a G, we could make it true because they could be two different numbers. But since they're both F, they would have to be the same numbers, and that wouldn't work, right? If we said F was 4 or F was 8, it's not going to work. It's not going to be equal on both sides of the equal sign. And last one, e times 1/3 equals e minus 3, or sorry, divided by 3. E times 1/3 equals e divided by 3. Can I make e lots of different numbers, only one number specifically, or no numbers at all? 13? What's the one number that would work? Guys, I need heads up off the desks, eyes open. I know it's Monday morning, but you gotta wake up. What's the one number you think could work there?
3.
Okay, so 3 times 3 would give me 3 over 3, which would be 1. 3 divided by 3 gives me 1. What if I did 6? If I made E6, 6 times 1/3 equals 6 divided by 3. Would that stay equal? What would I end up with if I did 6 times 1/3? I'd have to do what to the 6, everybody? Put it over 1. So then I end up with 6 over 3 equals 6 divided by 3. Are those equal? Yep, fraction bar is the same as division, right? So is it just one number? It's lots of numbers, right?
Can you just keep multiplying it by 3?
You could do any number and you're going to end up with the same division problem on both sides, right? Just like we talk about when we are dividing by half, or when we have to take half of something, we can multiply by half or divide by 2 because it's the same thing. It goes the same with any number. It could be 1/5 divided, and this could be divided by 5. Could be 1/7 and this could be divided by 7. It's the same thing that you're doing when you're multiplying by a fraction, a unit fraction, or dividing by the whole number. Okay? All right. We do have a home link, but we are behind since we didn't have electricity. So